All right, let's start. This is chapter 23 out of 25. এটা হচ্ছে the last big chapter, theoretical chapter. এরপরে দুইটা topic হচ্ছে it's just some information that you need to learn, medical physics and astrophysics. So right, this chapter is divided into two parts here. একটা হচ্ছে about mass defect and nuclear stability. This one is completely new for you guys. And the other one is something you have done before in your O levels. It's radioactivity. So it's like half-life and every other thing associated with uh, like decay. So yeah, this is your this, yep, this is the second part. This one is just four equations and the chapter is over. But this one is new, so I'll start with this today. I'll try to do the whole thing today. It's a very, very small topic, but completely new for you guys. Right. So, what does this deal with? This particular part of the topic deals with the stability of the nucleus. So, let's start to understand first with what the nucleus actually looks like and what's inside it. So, your nucleus consists of protons and neutrons, as you know from before. So, you have your protons and your neutrons. So, let's say right. So these are your protons and these are your neutrons. So the nucleus contains protons and neutrons. Now, the first question is, why does it need to have a neutron? Why can't we just have a nucleus just filled with protons? So it's a problem when your nucleus is exclusively protons. Protons are positively charged, and positive charges will repel each other. As a consequence, what happens is your positive protons here will start to move away from each other. There's nothing to keep them together. And that's a big problem. Why? Because the repulsion that the protons experience is immense. And you should be able to figure this out because you know how to find the repulsion between charges. So the way we find repulsion between charges is using F equals to K Q1 Q2 divided by D squared. So if you want to find the repulsion between charges in the nucleus, your K is 8.99 into 10 to the power 9 into charge of your proton is 1.6 into 10 to the power minus 19 whole square divided by the distance of separation between proton is arguably the smallest separation possible in the universe. It's just like just right next to each other, right? It's just smaller T2 gap possible now. So it's around like 1 into 10 to the power minus 21 meters and then square that. Once you put all these numbers in, you'll find that the force might not be very large, but I'll explain in a minute why it's important for us. It's something like, let's say, 1 into 10 to the power uh, 11 or 12 Newton. Now, you might think this force is not very large. Why is it considered to be such a large repulsion? Yes, the force itself is not very large. Uh, I mean, it is large, but it's like, not the largest force that we have heard of. But it's this force acting on a mass that is only 1.67 into 10 to the power minus 27 kilograms, which means when you apply this force on that mass, it's a very big amount of force. So as a consequence, your acceleration would be 10 to the power 40, for example. So it means that the protons are being pushed away with very large forces in every direction. And in theory, your proton shouldn't exist next to each other because the repulsion is very immense. Now, to keep the protons together, we have a solution, and we have seen this in O levels, that there is this particle called a neutron, and the neutrons come along and they create this bond around the protons, and they keep them together. So for every neutron, there is a proton out there, and they bind together, and that binding keeps them in their place. And this is known as the force, right? Is known as the strong nuclear force. It's the strongest force in the universe. And it is, if you remember from your AS, it is exerted by something known as the quarks. The quarks are responsible for this force. So it's called a strong nuclear force. Now, the strong nuclear force is what keeps the nucleus together. So yeah, this is the origin story of the nucleus. So the nucleus behaves this way and everything. আমাদের যেটা বের করতে হবে এই চ্যাপ্টার মধ্যে is what's the energy interaction? How is it stable? Why isn't every nucleus stable? Why is it that uranium is very unstable, whereas let's say something like iron is the most stable element in the universe in terms of its nucleus? That's what we want to see. So a chapter হচ্ছে main aim হচ্ছে ওইটাকে figure out করা. So before we start that, I'll first go through this discovery that we made. তাহলে জিনিসটা easier হবে. So what discovery am I talking about? So it turns out after physicists have derived and understood the structure of the nucleus, they wanted to find the mass of the particles. And they were successful in doing it. So protons and neutrons, এগুলোর mass বের করতে চাচ্ছিল তারা. And one of the ways they did was, let me show you. Right. So imagine I have this electronic balance here. And the electronic balance is capable of measuring the mass of the smallest things in the universe. Hypothetical একটা জিনিস, আচ্ছা? So yeah, you have this electronic balance here. It can measure really, really small masses of atoms and molecules. Okay, so this is the electronic balance. সো এই ব্যালেন্সটা দিয়ে আমরা কি করতে পারি? ম্যাথ বের করতে পারি, যে কোনো কিছু ম্যাথ বের করা যায়, যত স্মল হোক যত বড় হোক। ওকে, so let's see what happened. So what they did was they took this balance, right, and they placed a helium nucleus on it. Okay, literally না, just think of it as a example. So একটা helium nucleus এর ভিতরে you have two protons and two neutrons. So this is your helium nucleus, and there. And they took the helium nucleus and they placed it on this balance like that. And after they placed the helium nucleus on the balance, they got the mass of the helium nucleus here. So এখানে যদি mass check করো, এটা helium nucleus এর mass দেবে. And the mass can be shown very precisely, like only decimal places there. And they found the mass to be 4.0001675 4 U. So if you're wondering এটা আবার কি টাইপের mass, এটাকে বলা হয় atomic mass unit. Okay, relative mass. U is 1.67 into 10 to the power minus 27. So this is the mass of what? The helium nucleus. So তুমি যদি কোনো helium nucleus পাও, you place it on a balance, এই massটা পাবা. Okay, so this is proven. Mole number calculation অনেক কিছু করে we have found this. Right, so this is the mass of a helium nucleus. Now, the person doing the experiment thought, what if I find the mass of helium nucleus using its components? So, এটা যেটা দেখা যাচ্ছে, this is just finding the mass of the nucleus. তুমি nucleus থেকে একসাথে রাখলা. And this one is finding the mass of the nucleus components. So, how do you find the mass of the components? So what you do is you take what the nucleus is made up of. The nucleus is made up of two protons and two neutrons. Say আলাদা আলাদা করে দুইটা proton নিলা আর দুইটা neutron নিলা, and you place these two protons and two neutrons separately on the nucleus, on the balance. Sorry, এভাবে করে আলাদা করে রাখা। ওরা কিন্তু combined না. Be very careful about this. They're separate particles. Now the expectation was that same answer তো আসবে, কারণ হচ্ছে nucleus is made up of two protons, two neutrons. So if I have only two protons and two neutrons, the mass should be same here. Right? That's a logical way of thinking, right? And they saw the mass here, the mass of what? Two protons plus two neutrons are এটা ছিল the mass of a helium nucleus, which is also two protons, two neutrons. And when they found the mass here, they found the mass was, ওটার সাথে যদি compare করো, 4.00022 000 U. They found the mass was different. And not only that the mass was different, they found the mass was little higher. Now, this is a little strange. The reason why it's strange is because your nucleus of helium is made up of two protons and two neutrons, which is this, right? And this is two protons and two neutrons also, but massটা different হয়ে যায় সবসময়. And they found that this is consistent every time you take a nucleus. Okay, listen carefully. Every time you take a nucleus, তুমি নিউক্লিয়াসটা কম্বাইন্ড ভার্সনের ম্যাসটা দেখো, আর তুমি যদি ওদের ইন্ডিভিজুয়াল ম্যাসেস গুলো দেখো, you'll find that the masses are never the same. And this was called the mass defect. When they found this thing, they called it the mass defect. So mass defect is key actually. Let's first acknowledge that. So mass defect is the difference of the mass of the components, মানে এটা যেটাতে বানানো, mass of the components minus mass of the combined nucleus. So we found that the individual particles always gave you a higher mass compared to the components, compared to the nucleus. So এটাকে mass defect বলা হয়েছিল. So I'll define mass defect one more time, okay? এটা অফিসিয়াল ডেফিনেশন ডিফারেন্ট, বাট বোঝানোর জন্য এখন তোমাদেরকে যেটা বলতেছি ওটা শুনো. সো mass defect essentially is the idea that if you take a nucleus, ওটা যদি হচ্ছিল নিউক্লিয়াসটা কম্বাইন্ড ভার্সনের ম্যাসটা বের করো, লাইক ইটস কম্বাইন্ড, ইউ ফাইন্ড ইটস ম্যাস, একটা ম্যাস পাবা. তুমি যেটা ইন্ডিভিজুয়াল কম্পোনেন্টস এর ম্যাস বের করো, ইউ ফাইন্ড ম্যাসটা ডিফারেন্ট আসে. এন্ড খালি ডিফারেন্ট আসে না, সবসময় বেশি আসে. সো এই ডায়াগ্রামটা অনেকের জন্য হেল্পফুল হয়. সো বেসিক্যালি এই জিনিসটা হয়, দেখে তোমাদেরকে. This is combination, right? So the combination or mass are individual their mass. The individual particle masses is always greater than the mass of the components together. So this is always the case. So then came the question that I think you should be having. Why? Why is it like greater? Or একই জিনিস. So one, suggestion was that the nucleus probably had something extra, some other mass, but it doesn't. The nucleus just doesn't have anything else other than two protons and two neutrons. So why is it that the mass was different? And এটা করতে গিয়ে we realize something happening, which is when your particles are brought together, they bind together. Bind মানে they combine and join and become one. To bind, you need energy. There must be some energy requirement to bind and keep the particles together. And to do that, there's some energy requirement. Now, where is the energy coming from? কারণ এখানে তো হচ্ছে এই পার্টিকলটা আর এই পার্টিকলটা সেম in terms of mass, right? So as it turns out, when they combine, right, এই যে particles যখন combine করে, they sacrifice a bit of their mass to produce energy. So যেটা করে যে এই প্রোটন আর নিউট্রন যখন বাইন্ড হয়, there's a bit of mass lost. And a proton আর a neutron যখন bind করে, strong nuclear force, a bit of mass is lost. And that mass that's lost is the reason why the mass of the combination is little less. And we can use that difference in mass to find out how much energy was needed for binding them together. And this energy that's needed to bind them together is known as the binding energy. So binding energy হচ্ছে straightforward version হচ্ছে is the energy that keeps the particles together in the nucleus, like preventing the strong nuclear force from taking over, or the repulsion from taking over. Do you guys follow? So if you look at every element out there, right, you'll find that the total mass of the nucleus and the mass of its components, constituents in the nucleus, slightly different. And not only it's always different, you'll find that it's always more for individual particles than rather than combined particles. So it's always more when they're separated than they're combined. Right. So এখন হচ্ছে the thing is how do you find this binding energy? So to find the binding energy কি করতে হবে তোমাদের is this. So remember we found mass defect. So binding energy can be found using this relationship, which is mc square and del mc square, where del m is a change in mass. So you might have heard of this equation before, but I'll go through this equation one more time. mc square zeta. So according to Einstein, he came up with the relationship of mass energy equivalency. What is mass energy equivalency? So according to him, energy is equivalent to mass by the relationship mc square. So tomorrow mass can become energy and energy can become mass as well. So these are interchangeable. And to interchange them, you have this equation here, E equals to mc square. And yeah, that is the relationship. So anytime you want to see how much mass has in terms of energy, just the equation they use for. Second, in my scenario here, we have found that um, in the scenario provided here, we have found that your mass is missing. There's a mass defect, right? So a mass must have been converted to energy. How do you find the energy using this equation? Okay, mc del square. So binding energy is equal to the mass defect into c square. Mass defect into c square. And once we use this equation and relationship here, আমরা বের করতে পারি how much is the binding energy needed in the nucleus. So let me show you with an example. So আমি যদি এইটার binding energy বের করতে চাই কি করব? Let's try, okay? So binding energy for helium, let's say. Binding energy for helium. What do we do? So first of all, step number one is we find the mass defect. So how does one find the mass defect? You find the mass of the components individually, and then you find the mass of your particle together, right? So you can hocche 4 point, and I'll need your assistance here, 4.000200 U minus that one. So 4.000 167 4.00000016754U 54U. So yeah, that's the mass defect here. So what difference কত আসে? The difference in the two masses that you see here. Right. So 0.00034 sorry 3246U. That's the mass defect. Now this is in terms of U. So what you need to do is you need to convert this to kilograms. So mass defect is going to be 0.00 sorry 0.0003246 into 1.67 into 10 to the power minus 27 kilogram. That is a mass defect. And then from the mass defect, we want to find the energy, right? So therefore, step two is finding the binding energy. And to find the binding energy, you're supposed to use m del m c square. So del m is going to be this mass defect that you see here. So that into c square. So into 3 into 10 to the power 8 squared. এটা করলে যে এনার্জির ভ্যালুটা পাবা এক্সকিউজ মি ইজ ইয়োর বাইন্ডিং এনার্জি ফর হিলিয়াম। চেক করে দেখবা কত আসে এটা। Right, 4.88 into 10 to the power minus 15 joules. That is your binding energy for this nucleus. So that's how you find binding energy. So binding energy বের করার নিয়ম হচ্ছে you first find the mass of the components individually, then you find the mass of them combined, and then you find the difference in these two masses. That is called the mass defect. And then using binding energy equals to mass defect into c square, you can find the binding energy of this nucleus. So this is the energy that's available in the nucleus to bind them together. So এটা তুমি যখন হচ্ছে ওদেরকে combine করবা, এই এনার্জিটা লাগবে to keep them together. So yeah, that's what binding energy is. Now, what's the definition of binding energy in our syllabus? So the definition of binding energy in our syllabus is a little counterintuitive, but it's still the right definition, obviously. The definition হচ্ছে it's the amount of energy needed to separate the nucleons completely. So তোমার যদি নিউক্লিয়াস গুলোকে fully separate করতে চায়, take them away from each other as far as possible, যে এনার্জিটা লাগে is known as binding energy. The reason why it says counterintuitive is because when you hear binding, you feel like it's the energy needed to keep them together. But the way they define it in your syllabus is the energy to rip them apart, which essentially should be same. But if you need 10 newtons to keep two things together, how much force do you need to move them apart? 10, right? So similarly, if you need X amount of energy to keep them together, how much energy do you need to fully rip them apart? The same. So তার জন্য হচ্ছে তোমাদের সিলেবাসের ডেফিনেশনের মধ্যে they preferred the other version. So the version is that binding energy is the amount of energy needed to binding energy is the amount of energy needed to separate the nucleons completely, or separate the nucleons to a separation equal to infinity. So that's the definition they use in your textbook and syllabus. So anyways, that's your binding energy হচ্ছে concept. So this is this point here. Mass defect. There are So we went through this understand equivalence between energy and mass by E equals mc square, and use and define the terms mass defect and binding energy. So mass defect or binding energy এই মাত্র দেখলাম। Mass defect কি? Mass defect is the difference in mass between the nucleus of an atom and the components of the nucleus, মানে যেটা নিয়ে বানানো, that's mass defect বলা হয়। আর binding energy যেটা তোমাকে এইমাত্র বললাম, and this is how you find your binding energy. So binding energy বের করার নিয়মটা হচ্ছে এভাবে। Okay, so yeah, this is your binding energy concept. কোনো question থাকলে আমাকে বলো। Oh, the equation equals to mc square. We don't have the derivation for it. So আমাদের সিলেবাসের মধ্যে we just have to know the equation. So equationটা কোথা থেকে আসছে, let me explain. So this is called the mass energy equivalency equation. So what did Einstein say? Einstein came up with this theory that mass, like just whatever mass we typically know of, momentum আছে, mass এর হচ্ছে, you know, you have the quantity in kilograms, তারপর হচ্ছে it is occupied by all matter, এই সব কিছু যেগুলো mass-এর properties, right? Einstein said that mass, right, can be disintegrated and it can then form itself into pure form of energy. So it could be like gamma radiation or electromagnetic wave. So energy and mass are actually equivalent. They're actually the same thing. It's just that one takes the form of the other. মানে one or the other. দুইটা মধ্যে যে কোনো একটা নিতে হয়. So everything in the universe will either be mass or will be energy. And he said that the relationship between mass m and the energy that you have here is given by the relationship E equals to mc squared. So let's say you want to know how much energy your body possesses, right? Not the energy that you can consume, but all the matter in your body was converted to energy, right? How much energy do you have? So you'll put your weight here into 3 into 10 to the power 8 square. Then that'll tell you how much energy you possess. Turns out it's a really, really, really large number. করে দেখতে পারো. So that's the amount of energy every atom in your body will be able to provide if you were to entirely disintegrate. That's the idea. Now, why is this equation very famous? It was made very famous because this was the equation that they used to explain the nuclear bomb. The nuclear bomb, the nuclear weapon, right, uses this idea. Why? Because nuclear weapon মধ্যে, what it can do is it can take the mass and convert it to energy. And that's why, with a very small amount of mass, you can come up with insane amounts of energy. So back in the day when nuclear bomb was popular, people were told that this very simple equation that Einstein came up with explained the working of the bomb, right? But truly speaking, it's not his fault that the bomb exists. It's because people used other branches of physics to make it happen. যেটা আমরা শিখবো এখানে. But the core idea is this, okay? So E equals to mc square. And yes, the other way is true as well. তোমরা energy কে নিয়ে কিসে convert back করতে পারো? Mass এ. Both of these are actually true. So this equivalency of mass and energy is known as the E equals to mc square. Right. So that's your binding energy equation here. So there, I'll give the notes together so I get to that anyway. So yeah, there's a math here. Um, Same thing, or just আরেকবার বুঝাচ্ছি কি হচ্ছে এখানে. So this is the mass of the things combined. This is the mass of it individually. মানে two protons, two neutrons. নাম্বারস গুলো কিন্তু সব বানানো, আচ্ছা অ্যাকচুয়াল নাম্বার হচ্ছে তোমাদের বইতে কোয়েশ্চেন পেপারে দিয়ে যেরকম করে দিয়ে দেয় ওরা, the actual numbers অনেক ডিটেলসে দেয় কারণ চেঞ্জটা দেখতে হবে তো. So um, this is what the mass is supposed to be when they're combined together. This is the mass individually. Always individually is more than combined. And once we do the calculation, we find that there's a mass defect. And when mass defect use করে, we can find the binding energy of this atom. So yeah, this is what binding energy is. Now the question is what to do with this information. Like we now understand there's binding energy, right? But what do we do with this information? So I'll show you that in a minute. Okay. Right. So let's get back. Uh, what to do with this binding energy? So obviously, people thought, acha, binding energy is the energy that's keeping the nucleons together, right? So shouldn't that be an indicator of stability? Because if there's a lot of binding energy available, within that mean that that nucleus is more stable. So they started doing that. They started to investigate the idea of binding energy and stability. And that's where things got very strange. I'll show you right now, okay? So what they started to do is they started to plot a graph for all the binding energies out there and the different elements out there. Doesn't too much binding energy get it unstable to? No, no, no. Too much binding energy would be good, right? देखिए আমরা এখন. Because I'll tell you, binding energy is like glue. Okay, if you want to stick things together, right? Uh, Using glue is like binding energy. So if I use more glue, generally speaking, shouldn't it be better to keep my things together? So, if I have more binding energy, wouldn't that mean that my nucleus should be more stable? At least it should be more stable than the ones with less binding energy, right? So that's what we thought, right? And but as we started to investigate further, we found a surprising outcome. I'm going to show you that right now. So we found that if I plot a graph for proton number, like the different elements out there, versus binding energy. So এটা binding energy. Binding energy কে আমরা ইভি তে লিখি, মেগা ইলেকট্রন ভোল্টস, বাট যেহেতু এখন ওটা দেখেনি, জুলসে লিখে রাখি আমরা, ওকে? সো বাইন্ডিং এনার্জি বের করব, and we found that hydrogen doesn't have binding energy. হাইড্রোজেনের কোনো binding energy থাকে না. Why? Can you tell me? Why is it that hydrogen does not have binding energy in its nucleus? Right. There's nothing to bind. Hydrogen is just hydrogen, right? Hydrogen nucleus is কোনো neutron নাই. It's just a proton. So hydrogen is just an individual proton out there, right? There's no nucleus neutron out there. কোনো কিছু নাই to repel it. So hydrogen doesn't have binding energy, but hydrogen একটা isotope exists করে called deuterium. That's the first element we have that has binding energy in it. Okay? So I plot the graph for deuterium. And then what we start to do is we start to plot the graph for every element and their binding energy. So সব element গুলো binding energy নিয়ে আমরা plot করা start করি, right, to see how stable they are. And we find that the more the number of protons, the more the binding energy, which should make sense because that's how it should be, right? বেশি energy লাগবে. So you keep doing this and you find that more and more and more protons থাকলে binding energy বেশি লাগে. There's more repulsion. So you have to hold them together and everything. So এরকম দেখতে একটা graph পাই আমরা. The graph looks like this. So it kind of looks like binding energy and proton number directly proportional. See, that's how it looks like. Do you understand what I'm trying to say? So binding energy and proton number should be directly proportional like that. And that's what we found. But why was this surprising? It was surprising because down here was an element that is considered to be one of the most unstable elements out there. For example, plutonium, polonium, all the radioactive elements. So all the radioactive elements that you know, they were here. So, and they're very unstable, by the way. So you have your uranium. So uranium এখানে, তারপর হচ্ছে you have your plutonium here. All are very unstable elements, right? So the question then was, wait a second, আমার এখানে হচ্ছে I have some of the greatest binding energies ever, but these elements are some of the most unstable elements ever. What's going on? মানে how does that make sense that আমার energy অনেক বেশি but they're still unstable? Like something's up here, right? So this was the problem. So a genuine problem that when they looked at the binding energy relationship, they found that it doesn't really make any sense because more binding energy is somehow making it unstable. So what's the reason behind this, right? So the reason behind this is quite simple. I'll show you. So imagine I have this nucleus. That's a nucleus মধ্যে there are three particles and they're bound together by binding energy. So like that. Now I also have another element here. This element has four particles in the nucleus, a charta particle in the nucleus, and these four particles are also bound together like this. The bonds between them. It's a very oversimplified version, but বুঝার জন্য খুব দরকার, okay? Now the energy here is 5 joules, every bond, 5 joules, 5 joules. And the energy here is 4 joules, 4 joules, 4 joules, 4 joules, because charta, right? Now, if somebody asks you what's the total binding energy in this scenario, এখানে total binding energy কত, the answer would be how much? So binding energy total in this scenario is going to be 15 joules, right? Because 5 into 3, 15 joules. But if you look at the binding energy total on this side, you'll find it is a little higher. How much is it? 16 joules, right? It is 16 joules. Do you follow what I'm trying to do here? So I have found the total binding energy for both of them. And I found the total binding energy here is 16 and the total binding energy here is 15. So the question then arises, which one is more stable? The one with 16 joules of binding energy or the one with 15 joules of binding energy? What do you guys think? Konta beshi stable? Is it element A or is it B? Like, use your logic and try to figure out which one do you think is more stable? The one with higher binding energy total or Acha, okay. So the correct answer here is A, despite having less binding energy total, is actually more stable because we eventually realize that total energy doesn't mean anything in terms of stability. What means a lot is how much is the energy individually in the bonds. When individual bonds গুলোতে কতটুকু energy আছে, that is what matters more. And once we looked into that, we realized that, wait a second, এই তোমার এটার তো bonds গুলো more stronger than that. Yes, it has less energy overall, but individual bonds so stronger. So we now need to look into individual bonds. এই individual bonds এর নাম হচ্ছে binding energy per nucleon, average binding energy per nucleon. Okay, so binding energy per nucleon. এটা কেমনে বের করে? খুব easy. You just take the total binding energy that you found, which আমরা আগে যেটা বের করছি, total binding energy, and we divide the total binding energy by the number of nucleons. মানে আমার যতগুলো nucleons আছে ওটা divide করতে হবে, একটা average পেয়ে গেলাম. So we should take all the energy we get here and then divide it by the total number of nucleons. So আমি যদি এই helium-এরটা বের করতে চাই, like average bond কত energy carry করে, I'll divide this by 4 because there are 4 nucleons. And that's called binding energy per nucleon. And once we did that, it was a revelation. We found that there's a lot going on here actually. So let me show you key hoy. So once we plotted our graph for binding energy per nucleon versus your uh, versus your proton number, so the per nucleon of that one, the graph was very different. The graph was not increasing graph. The graph was like this. I'll draw the general shape. গ্রাফটা প্রথমে উপরে যায়, উপরে গিয়ে একটা পয়েন্টে পিক করে, and then it starts to go downwards. So যে এরকম দেখতে একটা গ্রাফ আসে. This is the graph for binding energy per nucleon versus proton number. And it's not the straight line that we anticipated. And this one makes sense. Why? Now, at the edge here, you have elements that are very unstable. So, a edge mode, you have elements that are like uranium, plutonium, polonium, and all those, right? So now we can find that there's actually a meaning to the graph because stability দেখা যাচ্ছে. So, যে এটা হচ্ছে unstable, এটা unstable. These elements are less stable, right? On the other hand, we also found that these elements are also less stable. এখানে you have deuterium, lithium, smaller elements below. Then the question was, which element is the most stable in this graph? And that means the most stable in the universe, right? So it must be the element at the top there. What element occupies that position at the top of your graph there? So it turns out the element that you find right at the top of your graph here has the most stable nucleus in the universe. Acha? So, when I say that it's the most stable, students will go like, oh, but I've seen that gold is more stable, or I have heard that reactivity series আছে একটা কেমিস্ট্রিতে ওইখানে তো আয়রন বা অন্য কোনো এলিমেন্টের কথা নাই. What is the stability you're talking about, right? So I'm talking about nuclear stability. Nuclear stability is very different from your chemical stability. Chemical stability is whether something will undergo a chemical reaction or not. That's not what we're dealing with here. ওইটা depends করে on valence electrons, about the structure of the electron shells, how easy is it for the electrons to jump and combine with somebody else. Reactivity series ওইটার উপর dependent. What I'm teaching you here is the stability of the nucleus only. We are not bothering about the electrons that the atom has. We are talking about just the nucleus and how stable the nucleus is. Turns out the most stable nucleus in the universe belongs to, do you know which element? Which element is the most stable nucleus in the universe? But out of all the elements out there, which element has the most stable nucleus? But in terms of its stability in nucleus, there is nothing second to it. Right. So it is iron. So the element iron, right, is the most stable nucleus in the universe. So why is it important for us? It's important for us because it means that your other elements in the universe will want to become iron, because the universe has this tendency to move towards stability. And every other element that you see out there, if they want to become iron, they'll have to do things to become iron. And that's what we're going to see right now. কি করে তারা? So right, one more time, our boli. Once we plotted the graph for binding energy versus the proton number, we found that it's not really revealing anything that's meaningful. কেন stability হচ্ছে না তো? We know that plutonium, uranium, these are very unstable. So why are they up there at the top? Because it's showing that they have a lot of binding energy. They must be more stable, right? But they aren't. But once we converted that information into a graph for binding energy per nucleon versus proton number, we found that it actually reveals what we normally know about stability. That these elements, like uranium, plutonium, are little unstable. These elements, like for example, your lithium, hydrogen, and other elements are also unstable, and the most stable nucleus belongs to iron in the universe. What's the implication of this? মানে এটাতে তাহলে eventually কি imply হচ্ছে? So it turns out there are things that these elements will do to become stable. For instance, elements which are light, these elements, right? Elements which are light would want to become iron. Can you tell me how can they become heavier? Smaller elements, if they want to become heavier, what do they need to do? Do they need to break down, or do they need to join up and combine to become heavier? So yes, I think kind of obvious, they'll need to join and combine to become heavier, right? So these elements that you see here on the right left hand side, they undergo this very important process to become iron, the process due to which we exist. It's called fusion. So it's called nuclear fusion. It is the process where small particles join together to become heavy elements. In the process, they release energy, because the more stable you become, the less energy you need to keep with yourself, because you're at a much more efficient level. So the energy ছেড়ে দেয়. And ওই energy যেটা ছেড়ে দিচ্ছে is what causes a star to burn. That's the source of energy in the universe. the hydrogen fusion process. So, right in the nucleus of a star, center of a star, the hydrogen fuses together to form helium, and in the process, it releases energy. Now, the helium in the nucleus, if you remember from your O level astrophysics, the helium in the nucleus will eventually also fuse together to form a heavy element. And they keep doing that until, do you remember when a star dies, what starts forming in its nucleus? Iron, right? So the moment iron starts forming in the nucleus, a star dies out. The reason behind that is একবার যদি আয়রন ফর্ম হয়ে যায় তাহলে তো স্টারের নিউক্লিয়াসে কোরের ফিউশন হচ্ছে না যেহেতু ফিউশন হচ্ছে না the star can't sustain anymore, so as a consequence যেটা হয় the whole thing collapses, right? So anyways, that's what happens when heavy elements want to become, sorry, lighter elements wants to become iron. They join together and they become this larger atom. But what about these, or what about the elements that are heavy already? How do they become stable? So the heavy elements, to become stable, they have to go the other way. মানে হচ্ছে ওদেরকে এদিকে যেতে হবে. And the way they go the other way is through a process known as fission. This is the one that takes place in a nuclear reactor. So in a nuclear reactor, what happens is, or like in an atomic bomb, what happens is you take elements like uranium, plutonium, polonium, and you trigger them so they start to break down and become iron. And as they start to break down and become iron, they're becoming more stable. And again, the more stable you become, the more energy you release. So যেটা হয় that they start breaking down আর ওই বাইন্ড করার যে এনার্জি দরকার ছিল ওটা তোরা লাগতেছে না, ওগুলা ছেড়ে দিচ্ছে and energy is released. So these two processes that you see here, one is called fission and one is called fusion. These are taking place so that the nucleus can become more stable. So stability gain করার জন্য এই জিনিসটা হচ্ছে. So this is the essence of our chapter. এই first পার্টটা কিন্তু একটু কি মানে if you look here এখন যদি যাই বলি number one কি equals mc square, টুটা পরে বুঝেছি ওটা ইম্পর্টেন্ট না. Three হচ্ছে use the term mass defect and binding energy. I've shown that today. Sketch the variation of binding energy per nucleon with nucleon number. That's what we just did. Explain what is meant by the term nuclear fusion and nuclear fission. ওটা তোমাদেরকে briefly বুঝালাম. Explain the relevance of binding energy per nucleon to nuclear reactions, including nuclear fission and fusion. এটা ম্যাথ একটা ম্যাথ আমরা করবো. And calculate the energy release in nuclear reactions using E equals to mc square. So that we will do as well. It's like the math. So mainly the essence of the chapter is what I just showed you so far. Okay. So yeah, this is the logic here between the binding energy per nucleon and nucleon number out there. So yeah, if you have questions on Kabbalah, let me clarify. All right. So, what is mass defect? These are definitions and everything. When we compare the mass of the components of an atom and the total mass of the atom, we find there's a difference in the mass. It is found that the individual components have greater mass combined compared to the combined one. And individuals গুলো সবসময় more mass থাকে rather than the ones that are combined. And this difference is known as the mass defect. The difference in mass is used as energy to bind the nucleons together. So the difference in mass কোথায় যাচ্ছে? Mass just can't disappear from the universe, right? So it must have been converted to energy, and that energy is known as the binding energy of an atom. And the binding energy is found like using this formula here, where the m is the mass defect. So what's the binding energy definition in your exam? It is the amount of energy needed to separate the nucleus and the nucleus to a distance of infinity. So completely separate করতে যে energy লাগে Yeah, it's called binding energy in your syllabus. Right. So this is the definition and everything. আর যেটা পরে দেখালাম ওটা হচ্ছে যে এটা, so এই যে x আর y এর মধ্যে which is more stable, so you'll find that x is actually more stable than y despite y having more energy here. So এই যে দেখো binding energy is not appropriate for chicken stability. So if you look at the total binding energy you'll find that it doesn't make sense কেন, এই যে uranium is highly unstable but ওর energy অনেক বেশি, আবার iron which is more stable ওইটা হচ্ছে মাঝখানে, so কেন এটা হচ্ছে? So the reason behind that is we saw the binding energy totally. But stability is not based on total binding energy. Stability is based on the binding energy of the nucleons individually. So how do you find that? So to find that, what you do is you take the total binding energy and you divide it by the number of nucleons that we have. And ওইটা করার পরে we get this graph here. Okay, so this graph is very famous, very important, and very often given in your exam. When we plot a graph for binding energy versus proton number, we find that proton number increases and the total binding energy increases. However, একটা পয়েন্টের পরে এটা আবার কমে যায়. And that's why it shows that 235 having very large binding energy is still unstable because per nucleon or অনেক কম binding energy. Okay? And elements that have lower binding energy will try to become iron. আর যেগুলা এদিকে heavier mass will also try to become iron. These will become iron by joining together. These will become iron by breaking apart. Okay, this is how the graph actually looks like. Okay, so আমাদের simplified version to শিখতে হবে. We learned that version. But মাঝখানে অনেক হচ্ছে এরকম ups and downs and exceptions exist করে. The most important exception is helium. Helium is surprisingly very stable. Look at everything else here, but helium is a peak here. So that explains the fact that when helium is formed, it is more stable, right? So that's the alpha particles that are formed. So when you have radioactive decay take place, a nucleus sheds off some of its mass, right? It could shed off any mass, but it decides to shed off helium nucleus, and that is because helium nucleus is more stable, right? So it's the best thing to shed off from the nucleus, and that helium nucleus is called the alpha particle. Right, so that is this আমাদের হচ্ছে next আমরা হচ্ছে nuclear fission and fusion process দেখবো. uh yeah, then we'll do radioactivity. So এটা হচ্ছে I will do one more time next class um তোমাদের এখন question থাকলে আমাকে একটু বলো, because my aim was to wrap this up. I thought I'll need like 1.5 hours, but তার আগেই হয়ে গেছে. But তোমাদের questions গুলো থাকলে আমাকে বলো, then it'll be easier for me to explain if there's anything that you didn't understand. What kind of questions? Questions গুলো খুবই ইজি হয়, and I really hope তোমাদের এক্সামে আসে. Questions গুলো এরকম দেখতে হয়, I'll show you. um তোমাদের রাইট এই যে এভাবে দেয়. সো কি বলছে এখানে, in a star the fusion of hydrogen into helium takes place and it produces your energy, right? Find the energy released. So কেমনে energy release করব, মানে বের করব? So we know that এখানে হচ্ছে you have helium, and then you have helium here and two hydrogen particles here. So we know the mass of these, we know the mass of those. Typically speaking, A mass আর A mass তো সেম হওয়া উচিত, বাট আমরা যখন এগুলা সব অ্যাড করি, আমরা দেখি there's a gap. সো কেমনে বের করছি দেখো, mass in মানে কতটুক mass provide করছো as 2 helium 3, right? মানে 5.008 এটা into 2. So we found the total mass that was given into the system. Then we found the total mass that came out of the system, which should have been same, right? But that's not same. You can see that there's a gap here. And a gapta is the mass defect. And according to Einstein's theory of energy mass equivalency, you can't just randomly have mass disappear. It must change into energy, right? So once you find the mass defect and use mc square, it tells you how much energy was released in the process. And that's the way you do this math. So yeah, typically mathটা এইটাই হয় where you have to find this এইটা আরেকটা example. এটা আমরা ক্লাসে করবো next ক্লাসে. So yeah, this is your binding energy concept. It's a very small topic, man. In terms of its core idea, it's just one idea that binding energy per nucleon leads to the stability analysis of a nucleus. And every element out there wants to become iron because iron is the most stable nucleus in the universe.